will come back and let's talk about the events of the second week of development. As you can see here, a revision for the events of the first week of development. Last week we talked about the implantation, and that was a summary for the first week of development. Now let me make sure that you understand that the first event in a regular 28 days menstrual cycle, on mid of that cycle, midday, mid of menstrual cycle means day 14 of this menstrual cycle, the Graafian follicle or the tertiary follicle would rupture under the influence, of course, of the hormone LH, and the secondary oocyte covered by zona pellucida, covered by corona radiata. As you can see, the red here is the zona pellucida, corona radiata, or what we call the cumulus ovoris. This structure only would be ovulated, and then at the same time this part of the fallopian tube, which is usually fimbriated, it has fimbria, and they are finger-like projections that would sweep over the ovaries to catch the ovulated egg. So ovulation, then the ovulated secondary oocyte would be caught by the fimbria, and then it moves through the fallopian tube, as we mentioned, and in its most dilated part, which is the ampullary part, it would be fertilized. So the here is the vagina is not drawn here. The site of the deposition of the sperms at the end of intersexual course. The sperms then would travel back to reach the oocyte. This would take place around, of course, in the ampullary part of the fallopian tube. So as you can see, here is the sperm. Actually, the drawing here is not 100% true, as the tail of the sperm should be staying outside. Only the head with the nucleus, it's all about the chromosome. The oocyte would provide the whole nutrients needed for the developing embryo, and therefore the journey from the ampullary part after fertilization towards the uterus would take about 3 to 4 days. Now at fertilization, which is the second event, ovulation, fertilization, we have restored the 2N structure. This is a somatic structure. This is the zygote. This is the unicellular embryo, or you can easily call it fertilized egg. Of course, it would move and would begin what we call the cleavage. What is the cleavage? It is a mitosis. Mitosis that increases the number rather than anything else of the cells. They become 2 cells, 4, then they become more and more. Of course, the drawing here is not that 100% accurate. However, as it reaches the way through the fallopian tube, it would become early morula. So it was zygote, then early morula, day 16 cells. This is about 3rd day of fertilization. This is the age of the embryo, 3 days only. which should be parallel to day fertilization 14, 15th, plus 3 days, that would be day 19, plus minus here, of the menstrual cycle. So we keep talking about two different things, the age of the embryo itself and the time of the menstrual cycle. Now, then the early morula would become late morula, as you can see here, 32 cells around day 4 of the age of the embryo, the fourth day of the development. So these days are the days of the first week of development. The first week of development begins from the moment of fertilization. So day 4 of what? Of development. Development of what? The embryo itself. Now this is the what we call the late morula. Now as the morula reaching the uterus, look at the uterus here in the secretory phase of the menstrual cycle. The gland are tortuous here, the arteries in the cross section, we talked about it. So it's the uterus is ready for implantation. So ovulation day 14, fertilization plus 1 day, 15th day of development of menstrual cycle, plus 3-4 days to reach the uterus. So we are talking about day 19, 20th of the menstrual cycle, and this is exactly the secretory period. And now we will reach the uterus day 5, as we day 5 of development, of course, and as it gets inside the uterus, the fluid here in the uterus would sneak inside the late morula, and the zona pellucida, as you can see, has gone, and the newly formed structure is nothing but a blastocyst. So that was the product of the final 5th day of development. We call it blastocyst. It was secondary oocyte, then zygote, early morula, late morula. Now the late morula has transformed into blastocyst. The blastocyst has embryoblast, 2 parts, and of course the trophoblast. And this is a lost structure inside the uterus. It has to be attached to here. Here all the food is here. Therefore the embryo would try to reach the uterine wall, and what we call this is implantation. By day 6, as you can see, the blastocyst would differentiate the trophoblast of the blastocyst would invade the uterine wall, and what we call this early pregnancy, which is early implantation. The embryo is not inside the wall. The embryo should get inside the wall for us to call it late implantation or pregnancy. So the female said to be pregnant, and this is the end of the first week of development. Now we shall talk about the second week of development with what is and here of course we will begin from the blastocyst. I already talked about it. That was the final product of the first week of development. The trophoblast, which is this structure here, and the embryoblast. This would give us the embryo, and this is where the future placenta would develop. So very primitive structure. This is the blastocyst. This is you by the beginning of second week of your life. You are a blast cavity with cells that they know that this is you, and these are the structures would look food for you, in from the uterus. Now, I strongly advise you to watch this video. It's important to reach out for any possible videos for embryology, and we will do this as we proceed. Now, at the 8th day of development, this is a cross section. So here you go. We are taking this, the embryo and part of the uterus. So this is a cross section here in the wall of the uterus. So this is the wall of the uterus. This is a uterine gland. So you can imagine how microscopic you were in the uterus. And of course, here is the blastocyst. This is the blastocystic cavity, trophoblast, the embryo blast. So let's have a look what would we have at the 8th day of development. The hypoblast, the epiblast, then the embryoblast. We said that the blastocyst itself has two parts, embryoblast here and the trophoblast. Now, the second week of development is the week of everything becoming two. So let's begin with the embryoblast. It would become two. Here the epiblast and here the hypoblast. Two things. And the trophoblast, let's go back to the trophoblast. This is the trophoblast, is also differentiating into two distinct cells. Those here are the cytotrophoblast, and here are the syncytiotrophoblast. Now, from now on, I shall break it to you. These cells are unique cells. They have no clear boundaries between them. Look at them, compare them with these cells. These cells, they have their cellular walls. You can see their boundaries here. But when it comes to the syncytiotrophoblast, you can't see this, and this is what gives them the name. They act as one syncytium, as one unit, and they are after these arteries. So I would like you to compare them, and I would call them for you as vampires. They are they are in a journey. They have a target, clear target, to get to these arteries. Now, let's go back to this cross section in the wall of the uterus. The embryo is much smaller than even a gland inside this wall, and the blastocyst has differentiated its embryoblast into epiblast and hypoblast. The trophoblast has differentiated into cytotrophoblast and the syncytiotrophoblastic cells. Day 9, and we're still in the second week of development. As you can see, the hypoblast gives rise to a thin membrane. Let me break it to you here that the epiblast will do nothing during the second week of development. The lights would be on the hypoblast. This is the main player during the second week of development. So we will talk about it later on, the epiblast, but now let's focus on the hypoblast. The hypoblast gives rise to a thin membrane, the exothermic membrane. This is the exothermic membrane. Now you need to go backward and to compare. This is the blastocystic cavity. This is the blastocystic. It's not lined by anything. It's just trophoblastic cells. We call them here cytotrophoblast. Yes, they are cytotrophoblast. But the cavity is named blastocystic cavity. Now the hypoblast would send some cells. Let me draw them for you here. These cells would line the blastocystic cavity here and here. There you go. What we call this membrane, we call it the exothermic membrane. Now this membrane did not reach the embryoblast here, but it did line this blastocystic cavity. And what was the name of this structure here? It was blastocystic cavity, as you can see it here. Now after it has been lined by these cells from the epiblast, of course, in this drawing here, the cavity has become the primary primitive yolk sac. Primitive yolk sac. You need to understand the blastocystic cavity. After the migration of these cells, the exothermic membrane, it became the primitive yolk sac. Now, the yolk sac cells form a fine loose connective tissue, the extraembryonic mesoderm. Now, I understand that these are new names, but you have to memorize them, as we will explain them later on. So what I am saying here in this slide, that these cells here, they migrate from the hypoblast, the exothermic cells here, they would form a extraembryonic mesoderm. So as you can see, this is that was the here inside this membrane would grow some cavities here. No, it's not gonna work like this. Cavities. So the yellow things here, the cells, they give extraembryonic mesoderm. This extraembryonic mesoderm lines all the cavity again, but it also reaches above the embryo here, the embryoblast, above the embryoblast, above the epiblast, sorry. Now, so let me just take you through what's going on here. It's easy, but you need to just keep focused. We had here the blastocystic cavity. The epiblast gives cells, the yellow cells here, and it becomes the primitive yolk sac. Then during the day 11, 12, the yolk sac cells send new cells that they form extraembryonic mesoderm. So this is a new layer around the yolk sac and around the embryoblast here, or the epiblast, and its amniotic cavity. We'll talk about it shortly. And this extraembryonic mesoderm which fills all the spaces between the trophoblast externally and the amnion of the exothermic membrane. So as you can see, it reaches everywhere. It fills this space everywhere. So now all of a sudden, day 11, 12 continued. Large cavities, look, it was solid layer here, extraembryonic mesoderm. All of a sudden, it would develop, as you can see here, cavities. These cavities would grow bigger and bigger, and eventually they would form a cavity. So the extraembryonic mesoderm was here, was a solid layer, as you can see here. Then cavities began to develop. These cavities has gone big and big, have gone bigger and bigger, and the extraembryonic mesoderm has divided into two layers now. One layer surrounding the embryo here, that's it, and the other one lining the cytotrophoblast here, cytotrophoblast. So, and you would understand that we have a new cavity here. This is the extraembryonic mesoderm lining the cytotrophoblast, and the amnion is called the extraembryonic somatopleuroc. This is the red one here, somatopleuroc, and the lining covering of the yolk sac is known as splanchnopleuroc. I will do it here. I'm afraid you will let's change the color, though it's not that much recommended. So this is the extraembryonic mesoderm that lines the trophoblastic cells. Now this, we call it somatic. Here you go. This is the somatopleuroc mesoderm. However, this one here, covering the embryo itself and the yolk sac, would be this splanchnopleuroc mesoderm. So the story is much easier than you would expect. The whole story begins with blastocyst. The blastocyst has a cavity. The embryoblast here has divided into epiblast, those cells, epiblasts, and hypoblast. The hypoblast would send cells to line the blastocystic cavity. Now the cavity has become the primitive yolk sac. Now these cells here, as you can see, primitive yolk sac here, these cells would give extraembryonic mesoderm. This extraembryonic mesoderm would be solid here, and this extraembryonic mesoderm would make vacuoles here, cavities, and as these cavities getting bigger and bigger, larger and larger, the extraembryonic mesoderm would split into two parts. The one that lines the cytotrophoblast, we call it somatopleuroc, and the one that covers the embryo itself here is this splanchnopleuroc mesoderm. But we already have a new cavity. What would you call this cavity? This is very important. This is the chorionic cavity. So the hypoblast produces cells that migrate along inside the exothermic membrane. These cells proliferate and gradually form a new cavity within the exothermic cavity. This new cavity is known as the secondary yolk sac or definitive yolk sac here. Of course, this would be the secondary yolk sac. And there you go. Here is the chorionic cavity. So, the key here is in that everything is dividing into two. I would come to this as we proceed. From the beginning, I said that this structure here, embryoblast, would divide into two, trophoblast and embryoblast, the whole thing. Now, during the second week of development, the embryoblast would divide into epiblast and hypoblast. Now, I haven't said this, maybe I've forgotten, that the epiblast also forms what we call the amniotic cavity. Amniotic cavity. So here, not only division for two parts, but also the appearance of the amniotic cavity. The cavity was here called blastocystic cavity. During the beginning of the second week of development, cells would migrate and line this cavity, and the cavity becomes the primitive yolk sac. So we have primitive yolk sac under the hypoblast. We have above and surrounded by epiblast is the amnioblastic cavity. So we have here two cavities. Now, as these cells, they here of the yolk sac, the primitive yolk sac, send cells as extraembryonic mesoderm. This extraembryonic mesoderm would surround the whole embryo, and even it would surround the amniotic cavity, and it would surround the primitive yolk sac. This extraembryonic mesoderm would have large cavities inside it, and it would split into, as you can see, two parts. This one here in black, I called it the somatopleurotic mesoderm, and this one here, this glandulopleurotic mesoderm, and the cavity between them is the chorionic cavity. What's this? It's the amniotic cavity. What's this? Now, that was the blastocystic cavity. When the cells migrated here, it became primitive yolk sac. When the extraembryonic mesoderm attached to it, it became the secondary yolk sac. So, primitive yolk sac, so it was like this, blastocystic cavity. Then, with the migration of these cells, it became the primitive yolk sac, and with the migration of the extraembryonic mesoderm, as you can see here, it becomes the secondary or definitive yolk sac, and this is what is written here. But we have also got a new cavity. This cavity is the chorionic vesicle here. The whole thing is called the chorionic cavity, the chorionic vesicle, and here is the chorionic cavity. Don't you ever forget that the whole embryo now is completely inside the wall of the uterus. Look, this is the embryo inside the wall of the uterus, and we call this complete late implantation. It could be at day 13 or 14 of the development by the end of the second week, and it would parallel the end of the menstrual cycle, which is day 27, day 28. Now, if you look at this drawing, you would understand that the extraembryonic mesoderm has formed something we call it connecting stalk, and this would be the future umbilical cord, and of course the whole embryo here is nothing but chorionic vesicle. So we have two cavities. This is the amniotic cavity, a secondary or definitive yolk sac. They are hanging through a connecting stalk in a chorionic cavity, and they all were just inside the wall of the uterus. So the embryo, the human embryo, does not develop in the cavity of the uterus, does not grow here, does not grow. The embryo would not grow here and getting bigger and bigger. It would get here completely intrauterine, the wall of the uterus, and then it would become bigger and bigger and would occupy the cavity. This is something we will talk about it later. So as you can see, new names, but let's talk about what is the final product of the second week of development. If you look at the embryo, so this is taken here. So if we take this, we would see that we have amniotic cavity, secondary yolk sac. How about the embryo itself? It has differentiated into epiblast and hypoblast, and therefore we call it bilaminar disc. So we have started with blastocyst, nothing but blastocyst, and we finished the second week of development by becoming bilaminar disc. We have two cavities, this cavity, amniotic cavity, secondary yolk sac. They are hanging to the extraembryonic mesoderm through connecting stalk which become the umbilical cord. So the bigger picture is that by the end of the second week, everything has differentiated into two, and the embryo itself is bilaminar disc. So this is you during by the end of the second week of your life, and you barely occupy anything in the wall of the uterus, as you can see here. You would just get inside the wall of the uterus. Okay. You are hanging inside a chorionic vesicle. That's a summary here. The second week of development is known as the week of twos. The trophoblast differentiate into cytotrophoblast, the syncytial trophoblast. The embryoblast forms two layers, the epiblast and hypoblast. The extraembryonic mesoderm splits into somatoplory, somatoploric and somatosplanchnic mesoderm, and two cavities, amniotic cavity and yolk sac, and all these structures they hanging from connecting stalk within the chorionic cavity. So what is the chorionic cavity? The chorionic cavity, it is a space between the created between the extraembryonic mesoderm that has attached itself to the embryo itself and to the cytotrophoblast from inside. Now, though it looks complicated, I understand, but you need just to memorize the last slide to know there are no too many informations in this lecture. It's a very short lecture, but I understand that you need to go through the names, the mesoderm, the hypoblast, epiblast. You need to know what these structures, as we will talk about them next week. All these structures mentioned earlier, you need to know their names. Now, it's time to talk about the chromosomal abnormalities, and this is a very complicated subject with many examples. It has been here reduced to its minimum, just to give you an idea what's going on. Of course, during your next year or third year, we will talk about the chromosomal abnormalities in details, but the abnormalities in chromosome number may originate during mitotic or mitotic divisions. So I have to say that here we are talking about the process of mitosis. For example, when the sperm is the spermatogonia becoming primary spermatocyte. So mitosis to increase the number. Meiosis, when we becoming from primary oocyte to secondary oocyte, from spermatocyte as well. So let's talk about it briefly. In meiosis, two members of a pair of homologous chromosomes normally separate during the first meiotic division, so that each daughter cell receives one member of each pair. So the example here is talking about not human cells, primary oocyte or spermatocyte. So you need to understand that this could happen in oocyte. It could happen it could happen in oogenesis and spermatogenesis. Let's put it this way. After the duplication of the DNA, 46 double structure chromosomes. Of course, here are representative cells. During division, we talked about this many times. We would get the one copy, one N here, one N here mixed though, and this is normal division. Second meiotic division, we would split sister chromatid, homologous sister. So this is normal, single, 23 single structured chromosomes. Now sometimes, as you have, I hope that you've at least got to understand what we talked about from the beginning of this course, that crossing over here could take long time. It begins during oogenesis inside the uterus. Then after birth, all females, they have inside their ovaries primordial follicles. What inside each follicle? Inside it an oocyte that has initiated the first meiosis 1, and it was arrested in prophase 1, meiosis 1 prophase 1 diplotin stage, and they're gonna stay there until puberty. So at least chromosomes would stay in this position for 14 years at least. Now, the first oocyte, which would be ovulated at age of 12, 14, at age of puberty, would at least its chromosomes would be crossing each other for that period of time. Now imagine if we are talking about a female that she is 45 years old and still having her menstrual cycle, and the oocyte reached its turn at this age. It means that this oocyte, its chromosomes have been crossing each other for the past 45 years. So can you imagine, when you will split them, some of them will not agree to that. Okay, so dare to split chromosomes that have been crossing each other for 45 years. Sometimes the crossing would not take, and however, separation does not occur, non-disjunctional. We cannot separate these chromosomes from each other during meiosis 1 or meiosis 2. This could happen in females commonly, and this could happen in males in less, of course, percentage. Both members of a pair move into cell. So instead of one color going to one cell, the homologous would take its homologous with it. So what does this mean? Let me just remind you, this is an example of non-human cells. Here we should have drawn 23 pairs of chromosomes, double structured, crossing each other. Now the chromosome number 1 has split it, chromosome number 3, 4, 5. It could happen that some of these chromosomes would not split. So we are talking about certain chromosomes. They won't split, and then therefore one of the daughter cells would have an extra copy, and of course the other cell would have that copy, and that's why here it's empty. This shouldn't be empty if had this been a human example. It could be 22 chromosomes, and here should be 24 chromosomes. Now in this example, the non-disjunction happened during meiosis 1. It could happen easily during meiosis 2. So now we have two things have gone wrong here. Supposedly this is an oocyte. It means that one of the daughter cells has an extra copy and the other one lacking a copy. And this would go into meiosis 2. And the result would be a cell with 24, a cell with 22 cells. So an oocyte with 22 or an oocyte and another oocyte with 24. This could happen easily during second meiotic division. Here we are talking about sister. These two cells, these two chromosomes should split. They wouldn't split. The two sister chromatids would go and form 24 chromosomes, and here 22, and you go also in this example. Now that could happen in the spermatocyte into the spermatogenesis or oogenesis. Now, luckily, we are talking about in males, one ejaculation we have 200 millions of sperms. So usually the fit one would reach the oocyte, but it could happen that a sperm with 24 fertilized an egg with 23. This is an extra chromosome. Or it could be a cell with 22, a sperm with 22 fertilizing an oocyte with 23. Then we're going to get 45 less chromosomes. And that's why we call all this here at fertilization, a gamete having 23 chromosomes fuses with a gamete having 24, or the opposite, 22 with 23. So either we have 46, 47, an extra chromosome, we call it trisomy. They should have been two chromosomes here, plus one of the chromosomes we just mentioned, one of the 23 chromosomes would take with it one chromosome. That's why we call it trisomy, or monosomy, or monosomy. It means one chromosome. So let's talk about real examples in our life. This is the Down syndrome, trisomy 21. It means that usually caused by an extra copy of chromosome 21, chromosome number 21. Look here, chromosome number 1 is normal, has its homologous 2 as well, 3, 4, 11, 12. However, when it comes to 21, obviously there is an extra copy. So 1, 2, 3, this is trisomy. And because it happens to the chromosome number 21, we call it trisomy 21, and usually we call it Down syndrome. Now, because Down syndrome is common, you need to know everything about it. Later on, you will know everything about it. But for today's lecture, we have to keep it very simple. 90% meiotic non-disjunction during meiosis of oogenesis. So here you go. I told you about this. Moms, they get blamed for 90% of meiotic non-disjunction during meiosis 2 of oogenesis, and only 10% of that meiosis of spermatogenesis. And we need to explain. I've been talking about meiosis and mitosis for you to understand what's going on, and it would be shame that you if you didn't get it. Why we blaming the mom? We shouldn't blame the mom, but here as an explanation for you, she has nothing to do with it. But because oogenesis has begun early intrauterine for the females, and it lasts for a long time. That's why chromosomes, they get crossed each other for a long time. When we take them, when separation is coming, they might not separate. And this is opposite to the male's spermatogenesis, which will we have stem cells, and they give you sperms within 60, 70 days. So the period of time chromosomes crossing each other in males much smaller than that of the female. However, having said that, 9-10% could be the father. And I'm sure I don't want you to memorize this table. I'm sure that you would ask this question, but you have to know that with age, Down syndrome, the possibility of Down syndrome would severely increase. Look at 45 years, one in each 25. That's why usually Down, they are associated with old parents who decided to have a baby at late age. But that does not mean that all old people they can get Down. As you can see also here at age of 15-19, the incidence is 1 in each 1,250, so you can compare for yourself. The message here, don't memorize this, you need just to understand that Down is the percentage of Down or the chances for Down to take place increases with age, and you need also to understand how to explain this as I mentioned it to you minutes ago. My message to you here, we have to understand that what is the difference between you and Down syndrome people. This is the irony that they have during their one of their parents during the preparation of the oocyte, usually in 90%, something has gone wrong. A chromosome did not split from his homologous chromosome, or a chromosome didn't split from a chromatid from its sister chromatid. Chromosomes, whether they are extra or we lack them, they are responsible for the synthesis of protein in our bodies, and therefore the copy is wrong everywhere in your body in the Down syndrome and Down people, and the consequence is going to be great. These individuals, what I know about them, that they are very kind and they deserve all the respect that you can give, and you need to care about them from now on. You need to know their story, you need to feel for them, and you need to be active in the society to care about trisomy 21 Down syndrome. Klinefelter syndrome, it's when something has gone wrong, the same story, but of course here we have also an extra chromosome related to sex chromosomes, phenotypically male with an extra X chromosome. Of course, I'm not asking you here to know anything about it, just read about it. It's another heartbreaking condition, and of course Turner syndrome. Here we have the XO, phenotypically female, missing an X chromosome. So this is of course a monosomy. The Down syndrome was trisomy. This is an example of monosomy. Turner syndrome is the only monosomy compatible with life. Even then, 98% of all fetuses with this syndrome would spontaneously die through abortion, of course. Few that survive are unmistakably female in appearance and are characterized by the absence of ovaries, gonadal dysgenesis. Of course, I don't know why we don't have here we have it here. It's another heartbreaking syndrome. I would leave this for the next years to be explained, but the idea here for me is very simple. We have gone through oogenesis and spermatogenesis in details. If anything goes wrong, we can get an extra copy of one chromosome and an extra copy of another chromosome, or lacking a copy of this chromosome or that chromosome, and they get the result when fertilization takes place. We're gonna have either monosomy or trisomy, and these conditions are very important for you as a doctor. I hope that these notes find their way to you, and next week we'll talk about the development of the embryo during the third week of its life. Thank you for listening.